Welcome to the second lecture on the series of heat transfer. In previous lecture, we have studied the introduction of the heat transfer. I hope you have seen that particular video lecture. Now let us start with the second lecture. So the objectives of this lecture are, after completion of the lecture, students will be able to understand thermal conductivity and heat transfer coefficient. Second, understand what is meant by thermal resistance in conduction, convection and radiation. And after that we have to solve some numericals on this particular syllabus. And unit objective number 3 and objective number 4 we will see in the lecture number 3. So let us see first what we have studied in the previous lecture. So in previous lecture we have studied what is meant by heat transfer and what is the application area. What is the application area of heat transfer? Application of heat transfer. Next we have studied what are the different modes of heat transfer. Modes of heat transfer, that is conduction, convection and radiation. What is the mechanism of each mode of heat transfer? Next we have studied what are the different laws governing modes of heat transfer. So in that we have seen that first law is for conduction, that is first law for the conduction is Fourier's law of heat conduction. Okay, so what is this law? Rate of heat transfer is directly proportional to that is equal to A into dt by dx, and that is equal to minus k into A into dt by dx. Okay, so we have seen this in detail, why this negative sign is taken, and already we have discussed what is this k. So what is this k? K is nothing but the thermal conductivity. Now today we have to see in detail what is this thermal conductivity and what is the unit of this thermal conductivity and what are the different variations of this thermal conductivity with temperature and pressure. Okay, now and also we have seen the next second law, that is Newton's law of cooling. Newton's law of cooling for convection. Okay, so in that what we have studied, rate of heat transfer is equal to H into A into delta T, that is Ts minus Tf. Okay, so what is this H? H is heat transfer coefficient. So we have to see in detail what is this heat transfer coefficient and what is the unit of this heat transfer coefficient and what are the different characteristics of this particular heat transfer coefficient. And also we have studied the third law, that is for radiation, that is Stefan-Boltzmann law. Okay, so now let us start with the today's lecture. So in previous lecture already we have discussed in the Fourier's law of heat conduction, that is rate of heat transfer is directly proportional to the area normal to the direction of heat flow and temperature gradient, that is dt by dx. So from this equation, if you modify this equation as k is equal to q upon a into dx by dt, neglecting the sign, and in this case if you put here the value of area is 1 meter square and temperature gradient, that is dx by dt or dt by dx as 1 degree Celsius, 1 meter per degree Celsius. Okay, then what will happen? Then this above equation can be written as k is equal to q. That means whenever there is a body and the surface area or the normal area to the direction of the flow is unity, and there is a temperature gradient, unit temperature gradient is present, then we can say that whatever rate of heat transfer will flow through that particular body, that is nothing but your thermal conductivity. Okay, so now let us define this thermal conductivity in detail. So what is thermal conductivity? So thermal conductivity is nothing but the amount of heat transfer through a body having unit normal area and unit temperature gradient. Okay, so this is according to this mathematical expression. Okay, so now next, or this can be defined as, thermal conductivity can also be defined as, it is the property of the material by virtue of which it allows the heat to transfer through it or to flow through it, or to transfer through it. So it is nothing but the property of that particular material. So if the thermal conductivity is higher, means what? That particular body or that particular material will allow the maximum rate of heat transfer through that particular body. Okay, and if the thermal conductivity is less, means what? That particular body will not allow, or will allow the less amount of rate of heat transfer through that particular body. Now let us try to find out the unit of this thermal conductivity. So we know that K is equal to Q upon A into dx by dt. So what is unit of Q? The unit of Q is watt, unit of dx is meter, unit of A is meter square, unit of dt is Kelvin. Okay, so this can be written as, or watt per meter Kelvin, that is meter get cancelled. So here we will get watt per meter Kelvin, or this can be written as watt per meter degree Celsius. So this is the unit of thermal conductivity. Okay, so now let us discuss what is the variation of the thermal conductivity. So now first in this we will see the variation of the thermal conductivity with temperature. Okay, so now let us see in first metals and alloys. Okay, so let us see the variation of the thermal conductivity in metals and alloys. So remember that as temperature increases, thermal conductivity decreases in metals except for iron. Okay, remember, in iron what happens? As temperature increases, thermal conductivity also increases. But for all other metals, as temperature increases, thermal conductivity goes on decreasing. Now why this happens? Let us see why this happens. So let us discuss this. Let us consider that, suppose when we heat this particular body at one end, what will happen? The whatever molecules are present at that particular point, that get excited. Okay, and due to the excitement of that particular molecules, what will happen? The molecule get vibrate about its axis. Okay, and due to the vibration, due to the lattice vibration, the collision of the molecules between two molecules takes place. Okay, now in metals what happens? There are large free electrons available. Free electrons are available in the metals. So the major carrier, the major heat carriers are free electrons. Okay, so whenever the temperature increases, what will happen? The free electrons get moved from one point to another point, and rate of heat transfer initially increases. But when the temperature increases beyond certain point or certain limit, what happens? The vibration is also increased. And due to the vibration, what happens? Whenever there is more vibration of the molecules, what happens? There is obstruction or the disturbances created to the flow of electrons, and that's why whatever amount of heat transfer should be takes place from one point to another point, that is not takes place. And that's why as temperature increases, thermal conductivity goes on decreasing. As temperature increases, thermal conductivity goes on decreasing. And this is the reason in metals why as temperature increases, thermal conductivity decreases. So what do you understand? As temperature increases, the disturbances to the flow of electrons takes place due to the vibration of the molecules. Okay, so this we have to remember. But in cast iron it does not happen. In cast iron, as temperature increases, thermal conductivity also goes on increasing. Okay, remember this. Now the thermal conductivity, the thermal conductivity initially decreases and then increases slightly with the increase in temperature. Now for platinum, the thermal conductivity increases with increase in temperature. So there is again exception, that is for platinum. As temperature increases, thermal conductivity goes on increasing. Okay. So these are the two exceptions. Now in non-metals what happens? Okay, in non-metals, let us consider in non-metals what happens. So as you know that in non-metals, for non-metals, what happens? The major heat carrier, the major heat carrier, the major heat carrier is what? The major heat carrier is lattice vibration, due to lattice vibration. Lattice vibration. So the heat is carried out from one point to another point in the non-metals due to lattice vibrations. Okay. So as temperature increases, consider if suppose we heat the non-metal at one end, what will happen? The vibrations get increased due to the increase in temperature, and there are no free electrons, so therefore there is no disturbance created, and as temperature increases, vibration increases, and that's why thermal conductivity goes on increasing in the non-metals. Okay, remember this. So in non-metals, as temperature increases, vibration increases, and that's why thermal conductivity increases. Okay, so this is in the non-metals. Okay, now what happens in the gases? Okay, this we have studied in the solid, that is metal and non-metal. What happens in the gases? So in gases, molecular collision increases with the increase in temperature. Thus, the thermal conductivity of a gas increases with increase in temperature. So in gases, we have to remember that in gases, the heat carrier is nothing but molecular diffusion. Okay, is molecular diffusion. Okay, so as temperature increases, molecular diffusion increases, and that's why thermal conductivity also increases in case of gases. Okay, so now here there are some thermal conductivities given here. So first is diamond. The thermal conductivity is in the range of 2300 watt per meter degree Celsius. For silver, it is 430. Okay, copper, gold, aluminium, iron, glass, okay, brick, water, wood, helium, air. So that means here, first, the thermal conductivity of the solid is more than thermal conductivity of liquid, then it is greater than again gases. Okay, but here if you observe the diamond, as diamond is non-metal, okay, diamond is non-metal, then the thermal conductivity is 4 to 5 times greater than the pure metal, that is silver. So why it is so? Though the diamond is non-metal, why the thermal conductivity is 4 to 5 times greater than the pure metal? So let us find what is the reason behind that. So as we have studied that thermal conductivity, okay, thermal conductivity is mainly depend on, okay, is mainly depend on the crystalline structure of the metal, structure of the material or body. Okay, now what happens in metals and non-metals, or in liquids and solids? What happens? The structure is amorphous structure is available in the solids and liquids. Okay, that means whatever molecules are available at the in the structure of the metals and non-metals, okay, that structure is amorphous. Means what? There is a random arrangement of the molecules. Is there. And that's why whenever one molecule get excited or heated, and due to that heat it get excited, and there is a disturbance is created to the transfer of heat from one molecule to the another molecule in all other metals and non-metals. But in case of diamond, what happens? Okay, let us consider this. What happens in the diamond? Diamond is highly crystalline in structure than other metals. The atoms are arranged in a highly ordered crystalline structure. These characteristics makes it possible to conduct heat easily than metals. Now, this is why the thermal conductivity of gases are much lesser than the liquids. So what happens in the gases? In gases, the molecules which are available at the structure that are very in randomness position. Okay, there is very much disordered molecules are available, okay, inside the gases, and that's why the thermal conductivity of the gases is very much less than the liquids. Okay, thermal conductivity of gases is very much less than liquid. Okay, and which is again very great, less than, which is very again less than the thermal conductivity of the solids. Okay, why? Because in solids what happens, the structure is well organized, but as compared to diamond it is not so much well organized. Okay, and that's why the thermal conductivity of the diamond is higher than the metals also. Now the molecules are far apart in gases. Thermal conduction is through the collision of molecules. Now next is what we have studied up till now. So in metals, okay, in metals and alloys what happens? The thermal conductivity is inversely proportional to the temperature, okay, except cast iron and platinum, except cast iron and platinum. Okay, in non-metals what happens? In non-metals, thermal conductivity is directly proportional to temperature. In gases what happens? Thermal conductivity is directly proportional to the temperature. As temperature increases, okay, as temperature increases, molecular collision between the molecules increases, and that's why thermal conductivity increases. Okay, so this is about the thermal conductivity in metals and alloys, non-metals and gases. Now let us see what happens in liquids. Now as we have seen earlier, thermal conductivity depends predominantly on molecular diffusion. Okay, so in particular liquids what happens? The thermal conductivity is again function of molecular diffusion, and as temperature increases, the randomness of molecular movements increases. This obstructs the transport of heat through liquids. Thus the thermal conductivity of liquids decreases with increase in temperature. Okay, so here again we have to remember that there is again a molecular diffusion effect is there in the liquids. So as temperature increases, the molecular diffusion increases. Molecular diffusion, what will happen? Increases, and this will disturb the flow of heat from one location to another location, and that's why thermal conductivity go on decreasing. Okay, but there is again exception for pure water. In case of pure water happens, what happens? Thermal conductivity first increases with increase in temperature and then starts decreasing. Okay, first increases, then it starts decreasing. Okay, so this is about the liquids. Okay, so in general we have to remember that thermal conductivity of the solid is greater than thermal conductivity of the liquid is greater than thermal conductivity of the gases. But here we have to remember that thermal conductivity of diamond is at the higher level. Thermal conductivity of the diamond is at the higher level. Okay, so remember this. Now let us see thermal variation of the thermal conductivity with pressure. So variation of the thermal conductivity with pressure. So as most solids and liquids are incompressible in nature, thermal conductivity does not vary with pressure. Okay, As solids and liquids are incompressible in nature, maximum solids and liquids are incompressible. That's why the pressure does not affect on this particular solids and liquids. But in case of gases, what happens? The kinetic theory of gases predicts and experiments confirm that the thermal conductivity of gases is proportional to the square root of the temperature T and inversely proportional to the square root of the molar mass. Okay, so here thermal conductivity is equal to or is directly proportional to what? It is directly proportional to the square root of the temperature and inversely proportional to the molar mass. Okay, as temperature increases, thermal conductivity increases, and as molar mass increases, thermal conductivity decreases. However, the thermal conductivity of gases is independent of pressure in wide range of pressures, okay, encountered in the practice. So remember, whenever there is large pressure range, then thermal conductivity is constant for that particular higher range of pressure. Okay, so I hope you understand up to this point. Now let us move towards the next point, that is heat transfer coefficient. Now, as we have studied in the Newton's law of cooling, that is rate of heat transfer, okay, Q dot is equal to H into A into T1 minus T2. And if you rearrange this equation, then we can write this as H is equal to Q upon A in bracket T1 minus T2. Okay, now here let us consider this. Let us consider this is the hot surface. Okay, and here we can say that this H is heat transfer coefficient is area exposed to the surrounding. T surface minus T fluid. Okay, this already we have discussed in the Newton's law of cooling. So, if you take this area, surface area as 1 meter square and temperature difference, that is the T surface minus T fluid or T1 minus T2 as 1 degree Celsius, then above equation will become H is equal to Q. So, what is meaning of this H is equal to Q? Whenever there is surface having unit surface area, that is 1 meter square surface area, and if there is a temperature difference of 1 degree Celsius, then whatever rate of heat transfer will take place from that hot surface to the surrounding fluid, that is nothing but your heat transfer coefficient. Okay, that is nothing but your heat transfer coefficient. Now remember here in this case, heat transfer coefficient is not a property. Remember, H is not a property of material. Okay, it is not a property of material. As already we have discussed that thermal conductivity is a property of the material, but here this heat transfer coefficient is not the property of the material. Now on which parameters it depends? Then heat transfer coefficient depends on, okay, it is an experimentally determined parameter whose value depends on first all the variables that influence convection, such as the surface geometry, the nature of the fluid motion, the properties of the fluid, and bulk fluid velocity. Okay, so these are the different parameters on which heat transfer coefficient depends. Okay, so now next is unit of H. So how to calculate this unit of H? So H is equal to watt upon meter square, watt per meter square Kelvin, or watt per meter square degree Celsius is the unit of heat transfer coefficient. Okay, so now, yes, already we have discussed these particular laws. Okay, already we have discussed these laws, that is Fourier's law of heat conduction, Newton's law of cooling, and Stefan Boltzmann law. Okay, so now what we have to do, we have to calculate the thermal resistances for this particular conduction, convection, and radiation. So now what is the thermal resistance? Now first let us see this. A rate of heat transfer is nothing but delta T upon summation of R, or this can be written as delta T upon RTH. This is nothing but your thermal resistance. Now as we have got the formula for conduction, that is Q dot is equal to K into A into dt by dx. Okay, so now if this can be written as suppose this can be written as Q dot is equal to dt can be written as delta T divided by this K bring this K to the denominator. So dx upon K, we can write this as like this. Okay, and if you compare this with delta T upon RTH, then what we get? Then here we get thermal resistance, that is RTH for conduction is equal to what we get here. If you compare this, then RTH is nothing but dx upon Ke, or this can be written as, if you take this dx as thickness, that is B upon Ke. Okay, so thermal resistance for the conduction we can write as B upon Ke. Now what is for convection? So now for convection, for convection we can write this as H into A into delta T. Okay, so if you modify this equation, then what we get? Delta T upon 1 upon HA. Okay, and if you compare this with delta T upon RTH, then what is value of RTH? Then RTH is equal to 1 upon HA. This is for convection. Okay, this is for convection. Okay, now if you try to find for the radiation, so what is formula for radiation? Q is equal to K, okay, into, that is F into sigma into A into T1 raised to 4 minus T2 raised to 4. And if you modify this equation, then what we get? F into sigma into A into A square minus B square. So T1 square minus T2 square in another bracket, T1 square plus T2 square we can write. And again this can be written as F into sigma into A. This is again A square minus B square. So T1 minus T2 in another bracket, T1 plus T2, and keep this as it is, T1 square plus T2 square as it is. Okay, so this can be written as indirectly. How? This can be written as Q is equal to delta T, that is T1 minus T2 can be written as delta T. Okay, so T1 minus T2 can be written as delta T upon 1 divided by here. Okay, what we can write here? Delta T upon 1 divided by F into sigma into A in bracket T1 plus T2 in another bracket T1 square plus T2 square. And if you compare this, then you will get the thermal resistance for radiation as 1 upon F into sigma into A into T1 plus T2 in another bracket T1 square plus T2 square bracket close. So this is the value of thermal resistance for radiation. Okay, now I hope you have understand up to this point. Now just we have write here same thing. So this is the thermal resistance for conduction, that is B upon Ka. We have to remember these equations. Thermal resistance for convection, and this is thermal resistance for radiation. Okay, so this already we have discussed. Now we have got the basics. We have completed the introduction portion, and now let us try to solve some numericals depending on this particular concepts. Okay, so now let us solve first example. Now what this example says? This example says that calculate the rate of heat transfer per unit area through a copper plate 45 mm thick, whose one face is maintained at 350 degrees Celsius and the other face is at 50 degrees Celsius. Take the thermal conductivity of copper as 370 watt per meter degree Celsius. Okay, so that is very simple question. Okay, look at this. So this is the suppose plate. The thickness of this plate is given 45 mm. After that, inside temperature is given 350 degrees Celsius. Other surface temperature is 50 degrees Celsius. Okay, thermal conductivity of this material is given how much? 370 watt per meter degree Celsius. And what they have asked? They have asked what is the value of rate of heat transfer per unit area, that is Q by A we have to calculate. And this Q by A is nothing but heat flux. Okay, this is nothing but heat flux. So this value we have to calculate. So very simple. So as there is a conduction takes place from one point to another point, okay, within the body, so that is q is equal to minus k into a into dt by dx. Okay, so this can be written as q dot is equal to k is given minus 350, sorry, not 350, 370. So this is 370 into area. Per area we have to calculate, so bring this area here, minus k into a into dt by dx. So dt, what is dt? Outer temperature minus lower temperature, that is, this can be written as 50 minus 350, 50 minus 350 upon thermal conductivity, thickness is given 45, so convert it into meter, so 0.045, and if you simplify this, then you will get the value of q upon a is equal to, that is rate of heat transfer per unit area, that will be equal to 2.466 into 10 raised to 6 watt per meter square, or this can be written as 2.466 megawatt per meter square. Okay, so this is q upon a, that is heat flux. Okay, I hope you understand this question. Okay, that is very simple question. Now let us move towards the next question. Again, this is example of conduction. So a plain wall, okay, 150 mm thick, and its wall area is 4.5. So let us draw this first. So 150 mm thick is given, area is given 4.5. Okay, if the conductivity is 9.35 is the thermal conductivity, inside temperature is at 150 degrees Celsius, outside temperature is at 45 degrees Celsius. Okay, determine heat flow across the plane wall. So here we have to calculate q, that is minus ka into dt by dx. Okay, so here we can calculate this as minus thermal conductivity is given 9.35, area is given 4.5, bracket dt, that is 45 minus 150. Okay, 45 minus 150 divided by thickness is 150, so convert it into meter first. So 0.150, and if you simplify this, then you will get the value of rate of heat transfer. Okay, that is equal to 29452.5 watt. So this is the value of rate of heat transfer through that particular body or that plane wall. Okay, next what we have to calculate? Next point, we have to calculate temperature gradient. So that is again very simple. So how to calculate temperature gradient? That is dt by dx we have to calculate. So dt by dx we have to calculate. So what is formula? Q is equal to minus ka into dt by dx. So from this equation, what is value of dt by dx? So dt by dx is equal to minus q upon ka. So q just we have calculated 29452.5 upon k is 9.35 into 4.5, and if you solve this, you will get the answer as minus 700 degrees Celsius per meter. Okay, so this is the value of temperature gradient along that particular plane wall, right? So I hope you have understand this question also. Now next, let us see the next question. That is question number 3. The following data relate to an oven. Thickness of the side wall of the oven is given. Okay, so let us consider this is the side wall of the oven. So 82.5 mm is the thickness. Thermal conductivity is given 0.044. Heat transfer coefficient 175. Okay, outer surface temperature 75, that is given here. After that, within the energy dissipated by the electric coil is given, that is q is given here, 40.5 watt q is given. What you have to calculate? Determine the area of the wall surface, so the perpendicular to the heat flow. So this is again simple question. So q dot is equal to minus ka into dt by dx. All quantities are given. So put the values here. Q is given 40 0.5 watt is equal to minus thermal conductivity. What is given? Thermal conductivity is given, what is that? 0.044. 0.044. Okay, thermal conductivity. Area we have to calculate into temperature. What we have to maintain? 75 minus 175 upon thickness is given 82.5. So convert it into meter, 0.0825. Okay, and if you solve this question, then you will get the value of area as area is equal to 0.759 meter square. So this is the surface area of that particular furnace wall. Okay, so remember this. So simple question again. Now let us try to solve the next question on convection. So let us consider this is the example of convection. So a hot plate 1 meter by, a hot plate is given 1 meter by 1.5 meter. Okay, that is given, is maintained at 300 degrees Celsius. So 300 degrees Celsius is given, and atmospheric temperature is given 20 degrees Celsius. If the convective heat transfer coefficient is 20, okay, that is H is given 20, calculate the rate of heat transfer. So here simple question, there is convection. Okay, so Q is equal to H into A into T surface minus T fluid. So what is H? Heat transfer coefficient is given 20. Area is 1 into 1.5 into TS, surface temperature is 300 minus 20. Okay, this is simple. Now if you simplify this, then you will get the value of Q dot, that is equal to 8400 watt, or this is equal to 8.4 kilowatt. This is rate of heat transfer. Okay, I hope you understand this simple question. Now next question is again of the convection. Now what this question says, a 1.5 mm diameter, okay, a wire 1.5 mm in diameter, 150 mm long, is submerged in water. Okay, so let us consider this is the wire. The length of this wire is given 150 mm. Diameter is given 1.5 mm. So if you convert this into meter, then 0.0, or this can be written as easily 1.5 into 10 raised to minus 3 meter. Okay, that is simple. An electric current is passed through the wire and is increased until the water boils at 100. So that means here we can say that the temperature of the surrounding fluid is 100. So T fluid is 100. Under the condition of the convective transfer coefficient, that is H is given 4500 watt per meter square degree Celsius. Find how much electric power must be supplied, that is what is the value of Q that must be supplied to maintain the wire surface, that is surface temperature of the wire should not be exceed 120 degrees Celsius. Okay, this is the question. That is very simple question. So here Q is equal to H into A into T surface minus TF. So Q we have to calculate. H is given, how much H is given here? 4500. Area, what will be the area? Okay, here area will be pi dl. Okay, area will be pi dl. So pi into diameter 1.5 into 10 raised to minus 3 into length is given 150 mm. So that will be 0.15 meter. In bracket, temperature, surrounding temperature should not be exceed 120 when the fluid temperature is 100. So if you simplify this equation, then you will get 63.6 watt. 63.6 watt. Okay, so this is the question. That is very simple question. Now let us solve the next question. That is again on the, I think it is on the radiation. Okay, so here it is mentioned. So a surface having an area, okay, area is given 1.5 meter square and maintained at, so temperature is given 300 degrees Celsius, exchanges heat by radiation with the another surface. So T2 is given, T1 and T2 are given 40 degrees Celsius. The value of factor, okay, that is F is given 0.52 and emissivity वो दोनों का मिला के दिया उन्होंने 0.52. Now determine what is the heat loss by radiation. So simple question. What is the formula? Q is equal to sigma into F, okay, into A in bracket T1 raised to 4 minus T2 raised to 4, isn't it? So whether area is given? Yes, area is given, so we have to assume that area. So what is value of sigma? 5.67 into 10 raised to minus 8 into factor is given 0.52. So 0.52 into area is given 1.5 meter square. T1, just remember here, many students make mistake here, that is this T1 and this T2 must be in Kelvin. Remember, here it is necessary to convert it into meter. So what will be this? 571, this is 571 and Kelvin, and this 40 plus 271, that will be 17, sorry, one second. So this will be what? I think this is 313, 313. 5, okay, one second. This is 573, sorry, 573, this is 273, this is 273, so this will be 313 Kelvin, okay. So now put these values and what we get here? That is 573 raised to 4 minus 313 raised to 4, and if you simplify this, you will get the answer as 4343 watt. 4343 watt, okay. So this is the rate of heat transfer due to the radiation, right? So now let us see the next example, okay. I hope this will be the last question. Now here this question is of combination of conduction, convection and radiation. This is the combination of conduction, convection and radiation. Now let us see what is this question. The question says that a carbon steel plate, the thermal conductivity is 45, 600 mm by 900 mm by 25 mm, okay, is maintained at 310 degrees Celsius, okay. So this is the plate like this, suppose, okay, this is the plate like this, right. The dimensions are given here. Let us consider this is 600, this is 900 and this is 25, okay. This is maintained at 310 degrees Celsius, okay. So this is the 300, this surface temperature is 310 degrees Celsius. Air at 15 degrees Celsius, temperature of air is given 15, blows over the hot plate. If the convection heat transfer coefficient is 22, so H is given 22 and Q due to radiation is given 250. 2 due to radiation, Q due to radiation is given 250 watt is lost from the plate by radiation. Calculate the inside plate temperature, okay. Calculate the inside plate temperature. Thermal conductivity is also given here. So as thermal conductivity is given, heat transfer coefficient is given, radiation heat transfer coefficient is also heat transfer rate is given. So that's why this question is of combination of conduction, convection and radiation. And what we have to calculate here? Calculate the inside plate temperature. That means this temperature is known to you 310. So what will be this temperature? Ti. This is the question. And this is TO, suppose, okay. So now, so here the heat balance equation is very important. So here we can say that heat conducted, that must be equal to heat convected plus heat radiated, okay. Whatever heat is conducted from inside surface to the outside surface, okay, whatever heat is conducted from inside surface to outer surface, that heat only convect and radiate. So this is the energy balance equation here, and that's why Okay, so what will happen here? So just we can write here Q conducted is equal to Q convected plus Q radiated. Now how to calculate Q conducted? So minus K into A into dt by dx. Okay, is equal to Q converted can be written as H into A into delta T, that is T surface minus TF, plus Q radiator is, that is given in the question directly. But here in this case, let us see which is the area. Now here if you see this plate, okay, like this, then which is the area of conduction? This area. Which is the area of convection? Again this area. And which is the area of the radiation? Again in that also the same area. So in all the cases area is same. Okay, in all the cases you have to take the area that is as same. And which is that area? So area is given 0 point, or here we can write this area as, because this length is 600 and this length is 900. So 0.6 into 0.9, that will be 0.54 meter square. Okay, and this is the area. Now, so if you put the values here, what we get? What is the thermal conductivity is given? 45. So minus 45 into area is 0.54, isn't it? In bracket dt. So what is dt? T outer minus T inner divided by thickness. What is the thickness given? 25 mm. So here we have to convert this into meter. So 0.025. Okay. So here what we have to calculate? Again here, 1 second. This TO is given to you. That is surface temperature is given to you. That is 310. Okay. So here unknown is Ti. Now that is equal to H is given. What is the value of H is given here? So the value of H given here is, I think, where is it? 22. Okay, so that is 22. So 22 into area is again same 0.54 in bracket surface temperature 310 minus air is flowing at temperature 15. So here it is 15. Okay, and plus 250 is given. 250 is given in the question itself. Okay, so now if you simplify this equation, if you calculate the value of Ti from this equation, then you will get the value as 313.86 degree Celsius. Okay, so this is the value of temperature inside the plate. Right, so now I hope you have got all the things. So what you have studied in this particular lecture? So in this lecture what you have studied, summary, let us see the summary of this lecture. First, what you have studied? We have studied the thermal conductivity, that is K, and variation of the thermal conductivity. Second, H. Okay, and what are the different characteristics, or on which factor, on which parameters it depends. After that we have studied okay, here after that we have studied the numericals, or thermal resistance, okay, in conduction, convection and radiation. Conduction, convection and radiation. And lastly we have solved some numericals. Now in next lecture